Who's had math today? Okay, this will be your second math class today. All right. So, talk math. We've got to, the way that we use math and science is different than what you guys have done in math class, because you've just done just pure numbers, right? It's just, I'm solving this problem, I'm rearranging this problem. Probably got some terminology that's overlapping with science, but how we use it may be a little bit different. Or how you guys look at a number and interpret it, well, there's no interpretation in math. How we interpret numbers is different than how we would treat them in math, okay? And the primary reason for that is because we're actually taking measurements. Our numbers represent something. It's not just some imaginary thing that has no meaning, okay? So, let's start off with a couple of questions. And I know this is not in your notes. I put it together this morning because based on past experience when I was thinking about it, I want to try to avoid confusion later on. So, you guys at home, I don't know if you can see that real well, so I'll read it. Is negative 10,000 a large number or a small number compared to negative 10?
Small.
Small.
Small number. Okay. So, and why do you say that? Who answered online there? Who was it that said that? Is that you, Lincoln? Or is it Jonah?
No, it was not.
I said it.
Why did you say that, Jonah?
Well, because the numbers are negative, negative 10 is only like 10 numbers below 0 compared to negative 10,000, which is like really tiny compared to 0.
Everybody okay with that? All right. And I'm not going to disagree with you. Your explanation is spot on. Your math teacher would be proud of you. This way. Okay. Is negative 10,000 a large number or small number compared to 1 million? Go ahead.
Large.
So negative 10,000 is large compared to 1 million.
Small.
Oh, wait, no. It's small.
Well, this is small compared to negative 10.
It's still.
I thought it was negative a million or whatever.
It's not negative.
Yeah, I thought it was for a second.
Okay.
So small.
So negative 10, based on the explanation that Johnny gave us before, it's still a small number. Right? Which is smaller, 10 or negative 100? Okay. So your math teachers in middle school taught you your negatives well. And that's fine. Here's the thing. In science, negative numbers, the negative sign is going to mean something to us. So when we see a negative number, it's not very often that we have measurements that fit on like a number line where you have positive values and then they change into negative values. The negative sign is there to give it some meaning rather than just being positive or negative on a number line. Okay? For example, who's in physics? Is there anybody in here that's in physics? Who's taking physics? Nobody? Okay. So in physics, you would use a frame of reference. So if I had a problem where I've got a person and they're going to walk a distance. In physics, the direction with which they walk is important. So if they go this way, we assign it a positive value. If they go this way, it's a negative value. The negative sign isn't meaning that the value is negative. It's just simply giving us a reference that they're moving in the opposite direction of the other. So so going left, sorry, is negative, going right is positive. The thing is, we can make this complete opposite. I know your instinct is to say, well, Mr. K, it's got to be on the left side negative and right side positive because that's what you've been taught with a number line, but it's arbitrary. It's kind of like up. Up for us is that way, right? Well, if you're on the opposite side in the southern hemisphere, antipode, that's what it's called, on the exact opposite side of the earth, up is that way, right? So it's arbitrary. So in science, our sign is giving us more of an idea of direction rather than anything else. So most of the time, our numbers are not numbers, they're measurements. And the positive and negative represent some kind of direction or some other factor that we're taking into consideration that are opposites of each other. Our numbers, though, size-wise, we speak of as more of a magnitude. How big is the number? Not on a number line, but just as an absolute value, what are the numbers related to each other? So if we go back up to this, and I look at the magnitudes, is negative 1,000 or negative 10,000 larger or smaller compared to negative 10 as a magnitude? It's larger. Even though it's a negative value, it is a larger magnitude because the number as an absolute is larger. Okay? So this is something we need to be aware of as we're going through and looking at the measurements and looking at the numbers that we're going to use, and that the positive and negative are not necessarily negative 10,000, I would say is bigger than 10, negative 10. Because I'm looking at it as a magnitude, not on the number line. Okay? Does anybody have any questions? Okay. Anybody at home, any questions?
I'm good.
No.
Good. Okay. Now, those of you at home, if you don't have the note, everybody actually, you need to have these notes so you guys can follow this. I had somebody ask me this morning to write that equation on the board bigger, and I asked them, well, why don't you have the notes up? Remember, you at home can have the Zoom and Notability or whatever up at the same time. Okay. So what we're going to talk about today is important because it lays a foundation for what we're going to do for the next 2 weeks or so. Okay? And it seems pretty, at the core, is pretty simple. We're going to be looking at attractions and repulsions, primarily attractions, but we're also going to look at some repulsions. But we need to look at the factors that affect those attractions or repulsions. This equation, V equals K, Q1, Q2 divided by D. I know science equations look scary because they got all kinds of different letters and subscripts in them, but this isn't that big of a deal. okay? Q1 and Q2 represent, like it says, the charge on the particle. D is simply going to represent the distance between those particles. V is going to represent the potential energy, and K is a constant. For us, since we're looking at atoms, and we're usually going to be looking at what is the effect on a single electron, so that we're all on the same page. My class, or this period 9, period 6, period 10, when we're plugging into this equation, if we're dealing with an electron, we're always going to deal with one electron at a time. So Q1 will always be negative 1. Excuse me. I have allergies really bad. Don't worry. Well, that's why I'm up here. You guys go back there too. All right, so Q1 for us will always be negative 1. Q2 could be negative 1 if we're talking about a second electron. But Q2 is more likely going to be dealing with a nucleus. Okay? Now, V, I said, represents potential energy. In your middle school science class, you were taught about potential energy. More than likely, the only type of potential energy you really looked at was potential kinetic energy. So you looked at potential energy, you looked at kinetic energy. So I have a can of Misty chalkboard and whiteboard cleaner. I don't use it, but I just have it. So holding it here, you guys learned it has potential energy, right? Now, if we designate this as 0 potential energy, remember it's arbitrary, okay? If I raise it higher, if this point's 0, if I raise it higher, it becomes a positive value, right? If I bring it down, it becomes a negative value. So we could have energies with negative values because we chose this point to be our 0. It simply depends on where you are defining 0. If we're talking about kinetic energy and dropping stuff, where is 0 potential energy usually defined as? Does that wake you up?
I realized you dropped it seconds after you dropped it.
Where is 0 potential energy generally for you guys? What about home? You guys got an answer? Where is 0 potential? If I'm going to drop something, where is 0 potential energy usually going to be defined as?
Once it hits the ground.
Exactly. Can that thing fall any further? No. So I can hold it here and I can drop it on the table. My potential energy reduced, but it's not at 0 potential energy like we would normally define it because we're not on the ground. Okay? What if I dug a hole? Is the ground now 0? No, but if I define it as 0 and I dig a hole and it goes down in the hole, it's now what? It's now negative. It's just where you define it. That's why I was going through we look at the magnitudes more than anything else. If I have the ground as 0 and I hold it here, this means I have this much potential energy above the ground. If I dig a hole and here's the ground and it's down here, then that much potential energy below the level of the ground. Okay? So this is how we use our negative numbers. They're compared to a reference point. How much kinetic energy does it have here? If I'm just holding it still, how much kinetic energy does it have? 0. Now, kinetic energy is a little bit different. You can't have negative. You can't have negative kinetic energy for the most part. Because if it's not moving, it has 0 kinetic energy. And you can't have negative movement. So if I drop it, I'm not going to drop it. I've rattled your nerves enough, it looks like. If I drop it, it starts to move, right? Okay. So those are examples of how we can have our potential energy as kinetic, how we could have a 0 value, how we could have a negative, how we could have a positive. But there are many types of potential energy. Chemical potential energy. Your iPads, for example, that you have or are using, they have an extraordinarily large amount of chemical potential energy. These things can run, what, 10, 12 hours. If you're careful with your power bank, right? You got your screen down low. You're not playing, 3,000 videos in the background. You don't have a bunch of tabs open. You can get these things to run quite a while. It takes a lot of energy to run that. I mean, your iPad is mostly battery. And that's where your energy is stored, if you wish. You have a chemical reaction that can take place that produces electricity that runs your iPad. Okay, K is a constant. Oh, back up. So our potential energy is the attraction part. How strongly are particles attracted to each other, or are they repelled? And this is our positive and negative. If you have positive and a negative, what are they going to do to each other? Wow, somebody said it. Positive and negative.
Attract.
Thank you, Lincoln. They're going to attract.
You're
If you
welcome.
have a positive and a positive, or a negative and a negative, what are they going to do? They're going to repel. Okay? Okay. K is constant. I did not put it on here, but K is always going to be a positive value. These are important, by the way, because we're going to do the math. And how the positives and negatives line up tell us a whole lot. D represents the distance measured between the particles and always a positive value. So unlike that diagram I drew on the board with the person walking, we're just measuring distances from this point to this point. That's it. They're not changed. And that can't be a negative value. You can't have a negative distance. Okay? Q represents the charge of the particle, and we know that they can have either a positive or negative charge. Electrons are what charge, class? Negative. Protons are what charge, class? Positive. Now, for us, the electrons are -1, protons are +1. Nucleus, though, is going to have more than one proton, except for hydrogen, so you could have a positive value that's not just one. Okay? We're going to build up to that. We're going to try and keep things simple here to lay the foundation for these relationships. Which gets us to this. This equation, I am not, there's like maybe 2 or 3 times where I'll ask you to plug numerical values into this equation and solve for them. For the most part, that equation is for us to look at the relationships between things. And for us, that primary relationship is how does it affect the attraction and repulsion? Is the attraction going to get stronger? Is it going to get weaker? Is repulsion going to be strong? Is the repulsion going to be weak? And the factors that go into determining that are our charges and our distance. So, in your math class, you guys talked about direct relationships, correct? Direct variation? No? Really?
I don't remember that.
You talked about linear equations? That's a direct relationship.
Yes.
Okay. So if I get a linear relationship, it's a direct because if I have the x-axis here, if I have the x-axis and y-axis, as the x value increases, so does the y. That's a direct. We talked about inverse. No? You see a graph like that? No? Okay. That would be an inverse. If you look at what's happening to the x and the y. As x increases, what happens to the y? Decreases.
Decreases. Yeah.
That's an inverse relationship. We looked at these relationships last time when we looked at the relationship between frequency and wavelength and frequency and energy. So frequency and frequency and wavelength are inversely related. As the wavelength gets really, really big, the frequency gets really, really low. And energy and frequency are directly related. As the frequency gets small, the energy gets small, and vice versa. That's an inverse relationship. You guys have done x to the minus 1, right? That's the inverse. That would be a direct. So if x went down to keep this the same value, y would have. What's the equation? The equation for a straight line is y equals mx plus b, right? Right. Okay with that? So where should B occur if we're dealing with data? If we're dealing with measurements, where should B occur? Actually, what is B first? In that equation, it's y-intercept. So where, if we're dealing with numerical data, if we're dealing with measurements, where should it cross the line? Where should it y-intercept at? At 0. So in science, we have all kinds of stuff that are linearly related, but we don't have a B because B is equal to 0. So if B is equal to 0, it just simplifies down to that. What is M? Slope, and does the slope change? That's what makes it linear. The slope doesn't change, it's a constant. So if I look at this line and I measure what's the slope here what's the slope here, or what is the slope for that entire part, they're all going to be the same thing. So this can't change, right? If I rearrange that equation and get y over x equals m, this is my constant. These are my variables. These are directly related. That's why it's linear. So you guys tell me you guys haven't graphed stuff on your calculators? Okay. I believe you. I'm surprised, but I believe you. All right. Any questions? People at home, any questions?
Nope.
No.
Thank you. All right, development of shell model. Magnitude is the absolute value of the number used to measure a quantity. We talked about that. So, assuming that Q1 and Q2 remain constant, so these don't change. It doesn't matter what they are. These don't change. What happens if the value of D is increased? What happens to the potential energy, this V?
The potential energy decreases
Why? You're right.
because in that equation you're dividing by d, and if you're dividing by a larger number, then the end result will be smaller.
There you go. Perfect. So if this goes up, the value for this is going to go down. This measures our attractions and repulsions, right? So if I have two particles, doesn't matter whether they're attracting or repelling. If I have two particles and they're either attracted or repelled, and then I move them further apart, what is going to happen to either that attraction or repulsion?
It's gonna weaken.
The weakening. You guys have done this. Who's played with magnets? Raise your hand. There we go. Good, Lincoln, you raised your hand. So all those other people at home, you haven't played with magnets. There we go. They're raising their hands. Lillian, you telling me you've never played with a magnet?
I almost choked on a magnet once.
Lincoln, you're not supposed to eat the magnets. You're one of those people that we read about in the papers, aren't you?
Yes.
Attracted, right? So obviously then, if I call this north, then this has got to be what? Okay. Or if this is negative, this has got to be. But if I flip this around, they're not attracted. I have to force them together. Okay? So in this case, if this is north, this is. And if this is positive, this is. So they're repelling each other. So if I have it like this, they're strongly attracted because they're really close together. But as I move them apart, wow, stronger than I thought. I can feel the attraction there, but as I get them further apart, I don't. Does that mean there's no attraction between these magnets right now? No, it just means it's really, really weak. Okay? Not enough for me to be able to feel it. Right about here is about when I can start to feel it. Very, very gentle, very, very light. Okay? So we know, because we've played with magnets sometime in our life, that distance matters. It's kind of like the game, you get the magnet on the fridge and try and get as close to the fridge without touching it. I know you've done it. If you haven't, it's your assignment over the weekend. Get a magnet, play with the fridge. Okay? All right. if the two particles are separated by an infinite distance, what value does V approach? It does not depend on the sign of V. The answer would be the same.
Is the answer 0? Or
Why?
it approaches because if the distance is infinite, then then it's got to be really small, and you can't go farther than 0.
Okay. You're right.
Unless you repulsion.
Well, even then you can't go past 0.
Yeah.
That's why here it doesn't depend. It's going to approach 0 either way. It's either going to get close to 0 as a negative value or close to 0 as a positive value. Because as we saw in the previous question, if this goes up, what happens to the magnitude for V? It's going to go down. So if I just keep making this bigger and bigger and bigger and bigger and bigger, this is just going to keep getting smaller, 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 smaller. Could it ever be 0? No. It can't be 0. But it can get so ridiculously small, we just say it's 0. Okay? Questions on that? All right. If D is finite, actually this confused people last time in class, or in period 2, period.
Wait,
What?
Mr. K,
What?
I have a question.
Go ahead.
So why
On the
wouldn't
previous
we
slide?
just write it as like, well, about the like basically being 0, why wouldn't we just put like 1 times 10 to the like negative infinity? Or like, why wouldn't we just write it like that?
That's actually a good question. In your math class, you would. Actually, in your math class, is anybody here in pre-cal? Anybody at home in pre-cal? Okay. So in calculus, this issue is addressed. And in the equations that you use in calculus, you do symbolize how that, it's approaching 0. So it's not necessarily you would write a number. You're absolutely right. We could write 10 to the negative infinity and take care of it that way as a numerical value. But for us in science, because these are measurements, we don't have instruments that can take us out that far. Our instrument's going to only be so good, and for the most part, it gets so small we just essentially say it's 0. We don't even worry about it. It becomes negligible. Okay? Does that answer your question?
Yeah, thank you.
Okay. So if D is finite, so it's not infinitely large, it's just some value. Okay, we really don't care whether it's large or small. It's just some value. If the particles have the same charge and sign, so Q1 and Q2 are the same thing. They got the same charge, same sign. Is V greater than 0? Is V less than 0? So if you're plug into that equation, and you had the same value for Q1 and Q2, Would V be greater than or less than 0?
Greater than 0.
Is that Logan?
Yeah. Hi, Mr. K.
How you doing?
Good.
So, Logan, explain why.
Because K has to be a positive number.
What about the others?
Well, if you have a positive number, you can't divide it by anything that would make it negative.
We can multiply it.
It's not the equation. What?
Well, yeah, there's 3 multiplications on the top.
But Q1 and Q2 would cancel out, wouldn't they?
Explain that a little bit further.
Well, if they're the same number but different signs, they would cancel out.
No.
No?
Can you see that okay at home?
Yeah.
Okay.
Mm-hmm.
Yeah.
So we've said K's got to be a positive value, right? Logan, what's Q1 and Q2 going to be? You make it up.
5.
5?
Sure, why not?
Positive or negative?
Positive.
Bring back memories of middle school. We had those equations where you had all these positives and negatives scattered everywhere because they were testing you on that PEMDAS crap. You know what I'm talking about, right? Logan, what's the answer that's going to be?
Positive some number, whatever it is.
Tell me what that number is. What's 5 times 5? Man?
25.
Okay, there we go. Positive
Still,
25.
okay.
I'm just assuming these are ones. What happens if these are negative? What's that? Same answer. Because if you have a negative times a negative, you get positive. If you have a negative divided by a negative, you get positive. So this tells us something. We now have a sign associated with V. If V is positive, and V is a measure of attraction or repulsion, and we just said V has to be positive if both of these are the same sign. What does the positive value for V represent? If I have 2 positively charged particles, and the value for V is, according to Logan, positive 25, because he chose 5 and 5. What are those 2 positive particles going to do to each other?
They're still going to repel.
So a positive value for V represents what?
The amount of attraction or repulsion.
Pick one.
The amount of it.
Because what do like charges do to each other? They repel. So a positive value for V means that there is a repulsion between the particles. What happens if I make this positive and I leave this one negative? What do I get? I get negative 25. And that means these particles are oppositely charged. They're going to do what to each other? Attract. So a negative value for V is going to represent attraction. It'll stop here. Yeah. You had a question? You had a question? I was just thinking out loud? Yeah. That's all right. So here's the thing. This is a really great illustration of how things we do in science are different than what you do in math. If I were to ask you, before discussing this, if I were to ask you to say, assign a value, positive or negative, to attraction and repulsion, what would you have assigned attraction's sign to be? Positive. But we're saying now, based on this equation, that attraction is a negative value because of how we're defining our variables. This is why, again, why we have to be careful about how we interpret a number as just a number in math versus a measurement in science. If I had a negative 25 and a positive 25, what that tells me is that their potential energy is the same but opposite. The attraction between a positive and a negative of 25, a negative 25V, the attraction between those two particles is the same amount of force as the repulsion between two positive values or two negative values that have a value of 5. Any questions? All right. Last slide, we're going to call it a day. If Q, an electron, Q for an electron is -1, then what will Q of proton be, class? Everybody, more in unison. Okay. If the Q of an electron is -1, and Q of a proton is +1, what is the Q of a neutron? 0.
0.
That's why they were difficult to discover, and they weren't discovered until like the 1930s. Most of these discoveries being made in the early 1900s with the electrons and stuff. It wasn't until the 1930s where we discovered neutrons, because if I were to throw a 0 in here, no matter what, V would be what? 0. Which means there is no attraction. There is no repulsion. So how in the world do you detect something that has no charge? I don't know. I didn't go to school long enough to find out. That's physics, people. Okay? But there's ways of doing it. Okay? Now, this one confuses people just because it's difficult to understand and read how it's being presented. But what this is asking is, what is the Q for a carbon nucleus? Just the nucleus. What's Q for the carbon nucleus? People here have a periodic table. I don't know if people at home would have one sitting in front of them. What's Q for a carbon nucleus? Why? Correct. Why? What's the atomic number tell us? You're right, more right the first time. You said electrons and protons. Yeah. So technically, the atomic number only tells us the number of protons. It tells us the electrons if they're neutral. And that's all we did in that first year. So yes, neutral atoms, protons and electrons are the same. But in just the nucleus itself, the atomic number tells us how many protons. Are there neutrons in carbon atoms? Yeah. Most of them have 6 neutrons, but do neutrons have charges? No. So the charge of the carbon nucleus would be +6. So if you're asked what's the charge of any element's nucleus, all you have to do is look at the periodic table and say what the atomic number is. And it would be positive that in the nucleus. Okay? All right. Does anybody have any questions on what we covered today? Because this is foundation laying for what we're going to do next week and into the week following. All right? You guys at home? Everybody good?
Good.
Oh yeah.
All right. So I'm done. I'm going to end it for you guys here. If you guys are online, going to log off now, you're more welcome to.